Okay, we've had our intermission. We're back. All right, so the total flux BA is this mu naught NIA. So if we look at this from a cross section, what we have is we've got our loop, and then inside of that loop, we have our solenoid, which has flux coming out of it or going into it, whichever way you want to draw it. And that amount of flux is just the magnetic field times the area, which is mu naught Ni, that's our magnetic field, times our area. Okay. The induced current, okay, if the current changes, when the current in the solenoid changes with time, then the induced EMF is the negative of the derivative of the flux with time, which is going to be negative mu naught N A.
You said changes with time?
Yeah, with time.
Oh, okay.
That's di dt. In other words, the part that's changing of the flux here of this mu naught NIA, the thing that's changing is I, right? We're changing that current with time. Okay. And that gives us an induced EMF. We get an induced current, which I'm going to call I prime, because I don't want to confuse it with the current in the solenoid, which is I. This is going to be the current in that single loop, and it's just going to be equal to E over R. So here's the question. What force makes the charges in that blue loop move? I said, what force is going to make the charges in the blue loop move? It can't be a magnetic force, because if you look at it, if you have a long cylinder, the magnetic field outside of the cylinder is zero. There's no magnetic field where this blue loop is. The magnetic field is all contained inside of the solenoid. So it can't be a magnetic force that's causing these charges to move. So the only other possibility is we have induced some type of electric field. There must be, they can't just spontaneously start moving. Charges don't move in conductors unless there is a force on them. So we've got an electric field. I'm not sure. I'm going to try to squeeze this in right here. I think it will fit. Let's see. Okay. So we know that work done by a uniform electric field on a charge can be given by QE, that's the force. The force is QE times the distance that the charge moves. In this case, that would be QE times, for one trip around, 2 pi r. If I take that and I divide both sides by Q, I get work over charge, which is our EMF, has to equal E times 2 pi r. Another way to think about that then, if we solve it, we could say that, gosh, our induced electric field would have to be equal to the EMF divided by 2 pi r. That's kind of what we did when we had uniform magnetic fields, where we would say it was the voltage divided by the distance. This is like the voltage divided by the distance. We actually are making an electric field inside there. I don't think I need that picture anymore. I'm going to bravely erase it. This is an interesting electric field in the sense it's different. This electric field is a non-conservative electric field. Why is it non-conservative? Because the work done depends on the path. In other words, when a charge here makes that whole circle and gets back to where it started, work was done on that charge. Normally, if you have a conservative electric field, you don't have any work done if you end up where you started. You'd have positive work and negative work, and they would cancel out. But that's not the case here. In this case, it requires work. If we take that and we go electric field and we integrate, we go all the way around it, that is our EMF. Or that has to equal the derivative of the magnetic flux. In other words, we've got two different ways to kind of find the same thing now. I'm going to add something. That's also E, right? This is Faraday's law. For a stationary integration path. Okay, this is just sort of a review. An electrostatic field is a conservative field. It's the result of static electric charge. What we just learned is that a time varying magnetic field produces a non-conservative electric field. This non-conservative electric field is called a non-electrostatic field. So it's an electric field, but it's different than the electric fields we studied back at the beginning of the semester when we had stationary charges. These stationary charges had these static electric fields. When you have this time-varying magnetic field, it actually causes an electric field, but it's a non-conservative electric field. The result of all of this is we kind of have three different versions of Faraday's law. I'm going to write all three of them just so you can kind of compare them and see what the difference is. Our original Faraday's law was just this, and this one always is true. Faraday's law basically says that the induced EMF is the negative derivative of the magnetic flux through some loop of wire. That's our original. We do have a version, though, of Faraday's law for moving conductors. That's what we came up with when we looked at motional EMF, where you're moving a conductor in a magnetic field. In that case, the induced EMF is the integration across this loop or path of V cross B, and then the dot product of that, dl. But that still has to equal the negative derivative of the magnetic flux. I mean, it's just another expression, but this is still equal to that. And now we have Faraday's law for stationary conductors, ones that are not moving. That says the EMF is the interval, closed loop, of that induced electric field, dot dl, and that's still that. I don't think you'll ever have to use these two. I mean, we might use them in an example, but you definitely have to use this one. And most of the time we'll use that one, we just have to stop and think, okay, what's flux? It's V, A, cosine phi. So what's changing, V or A or cosine phi? Okay. We're running a tiny bit ahead. Okay, I think we'll go ahead and keep going, and that way, I think next class on Wednesday, we can probably just review, which I suspect will be a wonderful use of our time, because we have a test then on Monday.
So. We also have homework 29 and the lab report as well.
Yeah, you've got a lot of stuff coming up. We're finishing up a lot of stuff, so we'll finish up our notes today, maybe not all of them, but we'll get close.
Well, those formulas are the same for moving and for stationary.
Did I copy the wrong one down for stationary?
I think they look the same.
No.
Because it was negative D and then the flux.
The moving one, this is moving, was the interval of V cross B dot dl.
Mm-hmm.
And that, of course, they all equal this. This is just Faraday's law that the induced EMF equals.
Oh, okay, so should I write that first part then too?
Yeah, you need this part, yeah. And then for the other one, that was this, which was E dot dl. It's this in-between part.
Okay.
And that, it still equals this. But it's more the idea of this part is different. That's moving, that's stationary. Okay. This last section deals with two ideas, really one idea and then just one kind of summary. So 29.7 deals with displacement current. And Maxwell's equations. Maxwell's equation is just kind of will be kind of a summary, but displacement current is something new. Let's consider a charging a capacitor. I'm going to think about what goes on when we charge a capacitor. So here's a capacitor. Make it a little smaller. So I have a little disc. And then I have a wire. I have some current coming in. I'm going to call it IC. That lowercase I is used when you have a current that might be changing, as opposed to capital I. And then over here I have a second disc. They're kind of exaggerated, but capacitors have that. And then there's that. So I've got a capacitor. All a capacitor is I've got two parallel plates. They happen to be round the way I've drawn them. And I've got current flowing in, and I've got current, I'm charging the capacitor. We have a name for this. It's called conduction current. And that's the kind of current we've been talking about, just current that flows through a conductor. The current causes positive and negative charges to build up on the capacitor. This one's going to build up positive charges, and this one's going to build up negative charges. Okay? If I draw a loop over here around this wire, I'm going to call that loop A. Loop A is going to have, there's going to be a magnetic field through loop A, right? Because every current carrying wire we know has a magnetic field. So loop A, around that current we call IC, has a magnetic field. That's given by Ampere's law. What's Ampere's law tell us? Well, Ampere's law tells us that the integral, I switch to blue here, of B dot dl is mu naught I, or in this case, enclosed, we're using a lowercase I. Okay, that's what Ampere's law says. Ampere's law says if you integrate a closed path around a current, the magnetic field is related to the amount of the enclosed current, right? What's the magnetic field of the enclosed current is 0. If I don't have any enclosed current, what should my magnetic field be? this is 0.
Well, if that's 0, then this is 0.
Then the magnetic field is 0, right? That's what Ampere's law says. Ampere's law says if you go around a closed path, if you contain some current, you're going to have a magnetic field. If you don't have any current, you don't, right?
That was one of the problems on the last one.
That seems reasonable. So let's look at this other loop. Let's look at loop B. I'm going to draw a loop B, and I'm going to try to draw it where you can tell that it's right here in this gap. I draw it beautifully, but we have another loop, loop B. According to Ampere's law, loop B will have no magnetic field. Good. It won't have any magnetic field because it doesn't enclose any current. Can't enclose any current. There's a big vacuum there, right? Well, strangely, experiments show that loop B has the same magnetic field as loop A. That's kind of a problem because it kind of looks like Ampere's law must be broken. But Ampere's law is not broken. There has to be something else going on. So let's think about, I'm going to have to erase this because I need to write some more. I want to stay where David can see it, but let's think what that means. I'm going to leave my picture, but I'm going to erase it just to make a little bit more room here. We know that electric fields are caused by, and we have two ways we can make an electric field. One is stationary charges. That's our electrostatic fields that we've always had. They make electric fields. And two is changing magnetic fields. You can make electric fields. We just did this less than 5 minutes ago. Anytime you have a changing magnetic flux through a loop. So, if we think about the symmetry in physics, then let's see, magnetic fields can be caused by one is currents. Same thing as saying moving charges. And two, that's where we're at. We understand that we can make a magnetic field with an electric current because that's what's going on right here. The magnetic field through A is caused by a current. But what could be causing a magnetic field right here? where we don't see any current. We don't even have a wire connecting the two plates. And so the answer is, well, we don't have a wire. But if we stop and think about it, as positive charge builds up on this plate and negative charge builds up on this plate, we're actually creating an electric field. And it's a changing electric field, right? As the charges increase, the electric field is going to get stronger and stronger. So the obvious answer is we must be able to make a magnetic field that's caused by changing electric fields. That's that symmetry. That means we've got some changing electric flux through that second loop, loop B, and that changing flux is causing there to be a magnetic field. Okay? Get this all straight in your mind, you're off to a good start. We know electric fields can be caused by stationary charges, and they can be caused by changing magnetic fields. Magnetic fields are caused by moving charges, currents, and changing electric fields. So as this charge is building up on these two plates, the electric field between the two plates is changing, and that's what's causing the magnetic field. But it's really interesting because the magnetic field measures to be the exact same size as the original, as if it was caused by a current right here. Okay? So Maxwell defined something called displacement current. Okay. The displacement current, which is the lowercase I, but it has a D. It is lowercase because we know that all of this only happens when the current is changing. When we're charging, that's going to change. It's equal to epsilon naught, and then the rate of change of the electric field. Or if it's not in a vacuum, it can be a plain epsilon. So for a vacuum, you put the epsilon naught. If it's not a vacuum, you have to multiply by the dielectric constant for whatever material's in there. The actual size, though, of this is always exactly equal to the conduction current. So it almost acts as if there's an invisible wire, like it keeps on, like the current's flowing, even though we know the current's not really flowing. Okay, that's going to change Ampere's law by a tiny, tiny bit. Oh, we're out of time. We'll pick up here next time. I'm going to stop. We are out of time.